Hello, this is a pre-recording of the slope exercise that's part of Geographic Information Systems in Water Resources for CUAHSI Virtual University. This is the PDF file that explains what the exercise is, the goal being to understand the calculation of topographic slope from a raster digital elevation model, the specific objectives being calculating slope from a digital elevation model and applying model builder geoprocessing capability to program a sequence of ArcGIS functions. This will work with data from the slope exercise data.zip file, which is provided in the course's Canvas website. There's three parts to this exercise. The first is the hand calculation of slope, and here you should be referring to the slides that were provided in the previous exercise that step you through what's involved and do calculations with this specific small raster of data, 5 columns and 4 rows, and calculate by hand the slope at grid cell A, which is the one indicated there. I'm not going to go through the hand calculations. I'm just going to point out the slides involved. So they start at slide 39 in this slide set. This just points to the definitions of slope and aspect from the ArcGIS Pro website. Then this slide is the one that you actually get the calculation, get the formulas that you should use in the hand calculation for the derivative slope method that's used in Esri software. This is a calculation of the corresponding aspect from that. And then the next slide actually steps you through an example. You should use these formulas with the data that's provided in the exercise. Then there's the calculation of hydrologic slope, which is the direction of steepest descent. And again, do these calculations with the data provided. And then there's a hand calculation of the d-infinity slope following the formulas given here. And again, you should follow the example that's given. So that's those are the slides that you should be referring to. I'm now going to close PowerPoint. The second part of the exercise after doing the hand calculations is to verify the calculations using ArcGIS. Now, there were some files provided in the slope exercise zip file, and I see that there's an error here that I'll correct this name in the file posted. But the slope exercise data zip file includes elif.asc, which holds this data that's shown on the screen here, and demo.asc, which is going to be used to check it for a large area. So the first thing we need to do is get this data out of the zip file into a location where ArcGIS can access it. And I have here a blank ArcGIS map project. I just created this project, gave it the name slope exercise, and it's got the base topographic map, but nothing else in it. So I'm going to switch to, this is the folder that corresponds to that project. And this is the zip file. I'm going to copy the files from that zip file into that project folder. Working with files in the project folder is a way to keep everything organized and together. So now that I'm back in that project, I can go into catalog, look at the folders. There's the slope exercise, and there are the two files involved. So the first thing we actually want to verify is the hand calculations that we had using this elevation data set. So I'm going to add this to the map with just the add data button, navigate through folders into the slope exercise, into this elevation file, and shortly this should appear on on my map. Since this is actually a data set that is not geographically positioned, it's got an arbitrary origin with the corner coordinates specified as 0, 0, as you can see here. It's not actually going to show up at any place sensible on the map. Rather, it's actually going to show up in the near the origin of geographic coordinates in the middle of the Atlantic Ocean. So once that file shows up as it has here, I'm going to remove the topographic base map because that makes no sense in the context of this project, and zoom to this layer. And here we're just seeing the individual data that was uploaded. I can click to verify that the values correspond to what was in the grid that was provided for the example. Sometimes there's a little bit of rounding here that means the binary representation of the number isn't exactly the same as what we saw, what was input, and that's just the way the numbers are represented and presented in the computer. We might actually also adjust the symbology of this to perhaps a color scheme that's a little bit more user-friendly. But the first thing to really do is to try and verify that this slope tool actually gives results consistent with our hand calculations, or verify that our hand calculations are actually correct. So if I switch into the geoprocessing panel, I open toolboxes, I can expand spatial analyst tools, and then there's a long list of things to choose from. I can expand surface, and this is where we find the slope tool. You could have also done a search in the find tools here, but I'm just showing you this interface because this also gives you exposure to some of the other tools that are available. So if I click on that, if we want to learn what this tool actually does, there should be a help button, and you can click on that and see what the read about what the tool actually does, and you can actually even go further into it and see the help information in the online help. So I'm going to select for this tool the input to be the elevation ASCII grid that we input, and on the output I'm going to just call the result slope, and I'm going to make sure it's going into I'm going to put it in the geodatabase for this exercise. And there's a choice here whether the output is in degrees or in percent rise. I'm going to put percent rise because that's what corresponded to the hand calculations, leaving the method as planar because this is not geographically positioned. There is a choice to go with geodesic, which will actually account for the curvature of the Earth. So with that all set, I will now use run, and the system will calculate slope for me. And you see the colors change in the middle 6 grid cells here. It didn't change for all of them. So if I turn off the elevation, you'll see that the values on the outside are not calculated. So what's actually happened is that it's only evaluated slope where there is actually where there are 8 surrounding cells. Slope is not evaluated on the edge cells because the formulas that we saw on the slide earlier depend on values outside of that domain. So we can click on the cell in the middle and see that the slope in this case is 11.4%. The next one down, 15.58%. and those should correspond with the calculations that you made by hand. The next part is to evaluate the aspect. So switching back out of the slope tool, there's the aspect tool also in the surface collection set. The input raster will be the same again, the elevation raster that we just provided. The aspect, I'm going to just name it aspect and save it in the exercise geodatabase. Leave the method as planar and run that function. And now we get a result, and the tool has symbolized the encodings based on degrees, 0 sort of north, northeast, east, and so on. And you can click on any individual grid cell. So for example, this middle one in the top gives an aspect value of 265, which if you look at the legend here, you'll see that it's in the range of being pretty close to west. 270 degrees, measuring clockwise from north would be going all the way around, almost to west, a little bit south of west. So this should again correspond to your aspect hand calculations. The next calculation that we wanted to verify was the hydrologic slope from the flow direction tool. So going back here, now that's part of the hydrology tool set within Spatial Analyst, and there it is, flow direction. So the input surface raster, again the elevation ASCII file. I'm just going to name the output raster floater, and there's an optional file to output, and that's the drop raster. I'm going to name that percentage drop, or just pers drop. If I look at the help information on that, you can read that the output drop raster is calculated as difference in z values divided by the path length expressed in percentages. So that's why I'm recognizing it as a percentage quantity and naming it so that I know that. And there's the choice of flow direction types. There's D8, there's D infinity that we spoke about, and then there's MFD. We're working with D8 and D infinity. So let me run it with the D8 options. And now we see it has actually evaluated quantities over the entire grid, and it's loaded into my map the percentage drop values as well as the flow direction. So for the grid cells along the edge, it calculated its best flow direction based on just using the cells that were available. That's a little bit of a shortcoming, in my opinion. I would have preferred it to have no data along the edge, but that's just the way it is. And you can click on some of these grid cells and see, for example, that this top grid cell, the percentage drop is 3.3% and the flow direction 8. There is at one point in these calculations where these numbers don't actually agree with what you get by hand. And if you've done the calculations carefully by hand, stick with your hand values. I believe the ArcGIS tool is showing an error in certain cases. So you can verify the percentage drop. You can also verify the flow direction at each of the locations A and B that we're interested in. And then we could repeat the calculation for D infinity let's name our output grids with the deinf at the end of the names, and then run it, and we should get now a separate set of results. You can see what the d-infinity percentage drop is, and also the percentage drop at that grid cell. So what I've asked you to turn in for this part of the exercise is a table giving the slope aspect, hydrologic slope, and flow directions at the grid cells A and B, which correspond to that one and that one, for all of the methods used. And also include some diagrams that explain or present your interpretation of what these values are. For example, show that the aspect is a horizontal angle measured counterclockwise from, measured clockwise from north, but the d-infinity flow direction is measured counterclockwise from east. So show that with diagrams. Show that the slope quantities are measured in terms of horizontal rise over run type of calculations. So then in this exercise comes a fun part. So we've effectively covered the first 10 pages of this exercise. Starting on page 10, we're going to now introduce Model Builder, which provides a convenient way to automate some of this processing. So we're going to develop a Model Builder tool to do this, and then you'll be able to effectively apply just with a few clicks the same method over different areas. So I'm going to go into this catalog panel of the map project, and there is a toolboxes folder, and whenever you create an ArcGIS Pro project, it always has a toolbox that's set up. You can right click on this toolbox and create a new model. So that opens this model window under the model tab. So if you want to get back to your map, you can switch there and switch back and forth between the map and the model. And the first thing we're going to do is it's going to be more convenient with the model to actually import our data that we're working with first from this ASCII format into an Esri raster format, and then have the model act on that. So we're going to find the ASCII to raster tool, which is in geoprocessing up here in conversion tools. There is to raster, ASCII to raster, and the way that one builds models is just finds a tool here and drags it and drops it on the screen. So there we see that it's created a little bit of this beginnings of effectively a flow chart, and there's the tool and what its output is going to be. So we can double click on it. Now there's a little bit of encoding here. The sort of rectangular things are actually processes. The oval objects are results, either input or output. So if I double click on this, it'll actually open a window that I can specify inputs, and I'm going to browse and find the, I guess for this project, the ASCII file we're working with. So I can specify that. The output raster I also need to specify, and I'm going to leave it in the geodatabase, and I'm going to call it ELEV M, and I'm going to put an M after to symbolize or indicate that it's model to avoid caching or overwriting the data that we already have in the system. And then there's a data type that I can choose, whether it should be integer or floating point values. Now we know that the numbers in this actually are decimal, so we choose float in this case. And when we click OK, so now we see that the things fill in, and blue indicates an input, green an output, and this orange is a process to be run. When the colors are filled in, the system is actually ready to go. So immediately after, well, the first thing that we actually did when we were doing the calculations by hand was run flow direction. So I'm going to now also add the flow direction tool to my model. So that was part of spatial analyst. Flow direction, I can again drag and drop it on the screen. And it appears also without any connections. And what we're actually going to do is take this elevation raster that we input and that is calculated by this tool and use that as input to the flow direction tool. That connection can be made just by dragging a line from the one to the other. And when I release it, it comes up with this window to say which input it's to interpret, and the top one is input surface raster. So I select that. Then the colors change because now all of the inputs are ready, and I can just control the I can control the colors, or I can control the names involved. So I don't want my output just to be called output flow direction raster, and this is gray because it's actually an optional output. If I double click on that flow direction tool, I can specify the output raster as flow dir from the model, and I can specify the output drop raster as burst drop with an M to indicate it's from the model. I can also choose the flow direction type. In this case, I'm going to go with the default D8. Later on, we'll add the D infinity one as well. So now this model is ready to be executed. There's two buttons here, validate, which will verify that all elements and parameters are valid. So I do that and I don't actually see any response. So we assume all is good. There's this run button. That means the model is ready to run. Now things happen pretty quickly here, so I'm not sure it'll be captured by the video, but when I click run, you'll see a window pop up showing progress, as well as some of these things will flash red as they're actually being processed. So let me click run. There you saw the one flash red, the other flash red, and this window shows that we get to completion. So this model has actually completed, and I can close this window here. Nothing actually changed. The results were not added to my map, and that's the default setting is for things not to be added to the map. But I can actually go into this catalog here, look at what's inside the slope geodatabase, and I may need to refresh it. And we should see somewhere the results. So I'm not seeing where the results were, so I'm a little bit puzzled by that. Maybe I didn't specify the location quite correctly, or maybe I need to look at this inside the database. Interesting that if you look at the slope exercise geodatabase, that's not showing it, but here it is. It may be that I've done this multiple times on my computer, and this may actually be the wrong database, or perhaps I need to refresh it there. Yes, if I refresh it on the folder there, I see the results. So no matter, there is the flow direction from the model and the percentage drop from the model. And if I switch back to my map tab, I could, for example, add them and then look at the results. So it's good to save this project periodically. So I'm going to do that. Sometimes these models, switching back to the model tab, can get a little bit messy. So there is an auto layout tool. And if I click that, you'll see the system rearranges it in what it thinks is a nice looking perspective. This exercise calculated not only flow direction, but also slope. So let me now start extending this model a little bit. And I'm going to go and find in the surface toolbox within Spatial Analyst, the slope tool. I'm going to add that to my model. I'm going to, as I did before, connect from elevation down to that slope tool, say that's the input raster. And I get to choose or specify the name of the output raster. So I can change that. I can click the slope tool. I can also click on output raster here to change things. And one has to be careful that you don't create name conflict. So for example, if I just put the variable slope and clicked OK, you would see that it's now showing slope 2. And if I'm clicking on that, there's a warning saying that slope already exists. I think if I run the tool, depending on what my geoprocessing settings are, it may just overwrite or it may give me an error, but it's best to generally avoid name clashes. So I'm going to go with the name slope M for the raster that's output from the model, and then we won't have any of those problems. So I'm up to page 16 on the exercise, and I'm now going to also load the aspect raster and connect it to the elevation grid. So we're going to say there's the input raster, and I'm going to set the output name from that to be just aspect M. And we also calculated flow direction using the d-infinity approach. So we are going to have a second instance of the flow direction tool, but now with the setting inside it to be the d-infinity type. So if I drag that and connect from the input raster to that, and now I can again go in here and set the results. So I'm just going to first set this to be d-infinity. The flow direction output raster, I'm going to call this flow dir I guess I'm going to call it flow. I see there's an error in the screenshot I have in the exercise. I'm calling the flow direction raster slope dinf, which doesn't actually make a lot of sense. So let me call it flow dir dinf m, and let me do the percentage drop as percentage drop dnf m to indicate that it's a model. And if I click on OK, so now I've got everything set up, but it's a little bit messy. Things are overlapping here. So I can actually click on AutoLayout, and it will all get organized nicely. So now we're at a point where I could actually click and run this and calculate everything all at once. So that's, let me do that. So let me first save in case there's a crash. The software's become pretty stable now, but in the early days we got crashes quite a lot. So it's always a good habit to save things. And now you'll see it's flashing through, doing all of the calculations that hadn't been done yet. Things that have been done already, it doesn't repeat. So now if we go back into my catalog and refresh my databases, we should see the results from everything, and I could load those to the map and check that everything's what I want it to be. So if I'm going to use this model the way it is, I actually have to come in right now and edit the inputs and outputs within this model. That's not the most convenient, and as indicated on page 17, one can actually set this up as to look like a geoprocessing tool by specifying the inputs and outputs as parameters. So I'm going to right-click here on this elevation and say I'm going to just make this a parameter. A little p appears next to it, and you'll see what the ramifications of this are in a minute. When we open a geoprocessing tool dialog for this, that file will be there that somebody can edit. We also want to do that for all of the outputs. So I can right-click on that and say this should be a parameter. Notice also that there's the add to display option. You saw when we were running the models, things weren't immediately added to my display. If I click this, that will then get added to display. It gets actually added to the display here, and it'll also remember that, so when you run it with different data, it's added. So I'm going to go and make all of the outputs along here parameters and add to the display. So there's a right-click parameter, right-click, add to display. Right-click parameter, right-click, add to display. Right-click parameter, right-click, add to display. Make that a parameter, add to display. Make that a parameter, add to display. And now the model is set. I'm going to save to save the model. So there's a number of save options. Save here actually just saves the model. Save up there saves the project. It's good to have everything saved. And you can actually close the model tab here, and it'll go away. If you haven't saved it and you try and close the tab, it will prompt you. So now we're basically just back looking at our map display, and within the catalog panel, you can see there's toolboxes, and here's our model. We could rename our model to something more meaningful than just model. So I'm going to rename it. How do I rename it? I have to right click there and go into properties and give it a name. And I'm just going to call it flow direction. It's actually flow direction and slope, but didn't want to have too long a name. And I guess you could password protect it. I've never tried to do that. So now it appears there as a with flow direction. I can double click on it to open it. And now a geoprocessing window with the name that I gave for it appears, and it's starting to populate some of the inputs involved as well as some of the outputs. So this is now set up to specify inputs using the dialogues that we're familiar with, and all of these have yellow warning signs because they've already been calculated. But let me just put a 1 at the end of each of those to make them different. Oops, didn't want to do that. Slope M1 into this aspect, put a 1 on the end of it, into flow direction, put a 1 on the end of it. So now all these names are different, and that's not because I'm too worried about protecting this data, because it's just a simple exercise really. But now if I run it, it should actually illustrate these being added to the map. So I can run it. So now the model is running. We don't actually see the model builder, but we see from these messages what's going on. We saw first the parameters involved, and as each tool executes, we get a report of its success. And now it's done, and you can see we've done all the calculations that we were doing before very rapidly, and all of the results have been added here. So we've got the percentage drop, flow direction, aspect, slope, and so on. So that's actually pretty cool. If you want to get back to the, perhaps edit your model some more, you can right-click here and edit. So edit brings us back to the model window where we could change things. There is the opens the geoprocessing toolbox, which is the same thing as double-clicking also opens the geoprocessing toolbox. So now you've actually created this model and could potentially use it for other data, and we're about to do that. So I'm going to save my project and close ArcGIS, and what I've asked you to do for this exercise is turn the screen capture of your final model builder. So what I want to do is, as the last part of this exercise, is run this with different data. So I'm going to open ArcGIS again, and so it takes a minute to initialize. Click on this slope exercise where we've been doing our work. So we're opening an existing project, and I'm going to close this map tab, which is pretty cluttered with all this work that we've done previously, and I'm going to open a new map. So I'm going to insert a new map that will basically be a new map that's completely fresh, and I'm going to load different data. So if I'm back in catalog here, we saw in the folder we were working in, the slope exercise folder, all of the work we've done was starting with the elevation ASCII file. Well, there is this demo ASCII file, which if you hover over that, you get a thumbnail sketch, which shows it's actually a different, bigger, more realistic data set, something that you might actually do this work for rather than that little test data set that we're really just using to learn how the software worked. If I load that onto the map, I can actually see what that looks like. Again, it's not geographically oriented, so I can zoom to the layer and it appears somewhere, and it actually thinks it's somewhere in I guess Eastern Europe, in Romania. This isn't really in Romania. This is actually data in New Zealand, but that comes about from the coordinates not being specified for this data set. So I'm going to ignore this by removing the topographic base map layer. And I'm going to go back to my model that's saved as part of this project and run the flow direction tool. And here I'm going to browse to choose the demo ASCII file as input, and choose new output. So where it says flow direction, I can put demo flow direction, set the other inputs according to the page 21 of the exercise. So demo percentage drop, demo slope, demo aspect, the d-infinity ones, demo slope d-inf, and demo percentage drop d-inf. What happened there? So demo percentage drop d-inf. So now I've set up these names, and if I run this, it will give me all of the results for this different layer. So let me go and do that. So there it shows me what the inputs were, and it's doing the various calculations involved, and soon we should see the results added to my screen. So there, I've run it for a different data set, a different location. I've automated what could have been a fairly tedious manual process, and yeah, there I've just used Model Builder and built a model. Now there's obviously some refinements to be done. You will see that the names that were put there were what we actually used in building the model, and they're probably not very intuitive to. So if you were to distribute this model to somebody else, you'd want to go in and edit these to give more meaningful guidance as to what people should put there. We could have these files not be input by default, but have them be empty and have the user choose them. So there's more work that can be done to refine that. And if you're going to be doing a lot of work with Model Builder, I'd encourage you to learn how to do that. But I just wanted to, for this exercise, expose you to some of the power of Model Builder in terms of automating the sort of calculations that we have here. To sort of verify that you actually got this far in the exercise, I've got to ask you to turn in the minimum and maximum values of each of the 6 outputs from that model, and you can read these off the legends here, or you can actually look at the properties of one of the layers and say go into source and raster information. You can see, I guess it's probably in band method. I'm going to guess it's in statistics. If you look in statistics, you'll see there it gives minimum and maximum values involved. So those are the sort of things I just put in a table to turn in. So that's this exercise. And I'll sign off now, and you can do it. Good luck.